Welcome to the fourth video lecture in this series of introductory videos about compilers. And the goal of this lecture is to talk about how is it feasible to write a compiler from scratch in the time we have. So starting with homework 1 through homework 4, how is it possible that we can build a compiler from scratch? And the answer is we exploit a lot of work that has gone into compiler design and clever algorithms that have been constructed in order to make this a feasible task. So the first insight is that programming languages, even new uninvented programming languages, still have a lot in common with other programming languages. So there's commonality among different programming languages. The languages might look very different, like Java might look very different from C++, but underlying Java and C++, there is still common properties that we can exploit in order to make it feasible to analyze many different programming languages. Not just the ones that exist now, but programming languages that will exist in the future. So the idea is not to write a compiler for a particular language. So if I give you a new language, let's say, I say, here's a language called decaf, go write a compiler for it. First thing you do is not open a text editor and start writing code. The first thing we do is try to figure out, well, what are common things between this programming language and previous ones? Can we actually create a generic tool that helps us write a compiler rather than just writing one from scratch? So the key insight in compiler design is you sort of use and exploit a general mathematical model for the structure of all programming languages. What makes it easy is we implement a compiler using this model. And essentially what we're doing is creating a new kind of programming language. And this programming language is built for writing compilers. So essentially we're writing a compiler that will help us write compilers. So again, this sort of meta level reasoning that we've been hitting on throughout these series of introductory lectures. Compiler tools that have been studied and built are called compilers. So this idea of using a compiler tool to build a compiler is what we're going to exploit in this course. And the most famous one is called YAC, which stands for Yet Another Compiler. The actual version of YAC, which is an implementation of the same algorithms, but the program itself is called Bison, and Bison is a re-implemented version of YAC from the GNU project, which GNU stands for GNU is not Unix, recursive acronym. We computer scientists like these meta-level recursive things. We put them in our acronyms as well. We also use a higher level representation of assembly language. So we create an intermediate assembly language, or IR. Yeah, behind this is there's lots and lots of different chipsets. So there's x86, there's ARM, etc. Doesn't make sense to do code generation for each chipset separately because there's a lot in common among all of these different chipsets. They all use the von Neumann architecture. They have registers, they use memory, they load and store from memory, etc. There's a lot in common among these different computer architectures. So again, we exploit this commonality and use an intermediate representation for all of these different architectures. So we don't have to reinvent code generation for every new chipset that comes out. So this allows us to make code generation as well a lot more efficient in the sense of minimizing the amount of time it takes to write code generation. The other advantage of IR is that code optimization ideas, so how to make code faster, can be shared among all of these different architectures. We can take this high-level ideas of code optimization, apply it to IR, or the intermediate representation, and now all of these different architectures can benefit from these optimizations. So the main requirements in writing a compiler is that there is a cost to compilation and there's a cost of executing the code that's generated. And there are often trade-offs that you have to make. You can spend a lot of time and do a really good job of code generation, but you don't want the user of the compiler to hang around for too long. They can get impatient. So all of these trade-offs between speed versus accuracy have to be managed when writing a compiler. But what's non-negotiable is that if there is a program and it's not a valid program, then you shouldn't generate code for it because that's very dangerous. You need to generate code only if the program is valid. Otherwise, you can sort of create invalid output which doesn't match what the user intended in the program. So no program that is invalid according to the programming language specification should be passed through the compiler and succeed. And the converse is also true. If it's a valid program, then you shouldn't reject it, because that's very frustrating. As a programmer writes a program, sends it to the compiler, and the programmer knows it's a valid program because they've studied the language specification, but the compiler says there's an error. That can be very frustrating. In order to build a compiler, there are some basic requirements that you need, data structures, etc. So the main data structure that's outside of the standard compiler toolchain is symbol table management. So you need a data structure that will store the symbols and link the symbols together within the same program. Remember that linking symbols across different programs is done by a separate stage called a linker. We also need to make sure that we detect errors and report them. So we need some kind of error detection and reporting infrastructure. So we need to write code for that. So there are two stages, broadly speaking, in a compiler. The analysis stage, where we are trying to understand what's in the program and understand its structure, which is called the front end. From this front end, we get some output, typically in a tree structured format. And then we traverse that tree and generate the code for that program. And that part is done in the backend. So the synthesis part, generating code, is done in the backend. So there are many different stages of the compiler, and what I want to do in this lecture is sort of give you details of each of these stages. So the front end is split up into lexical analysis, syntax analysis or parsing, semantic analysis or type checking. The back end is split up into intermediate code generation. So this generates the IR or intermediate representation. And then you do code optimization, and then finally code generation. And code generation produces, for example, x86 assembly. And that then is converted to machine code and run as a binary executable. So graphically, this is what it looks like. These are all the stages in a compiler. And in this course, we're going to study every single stage of this pipeline. So we're starting with lexical analysis, then going to syntax analysis, semantics, intermediate code generation, code optimization, and then finally code generation. So you can see that there is a split here. This is on this side of the split is the front end. On this side of the split is the back end. And overall, the stages, we have a common data structure called the symbol table that manages all the names of things, names of functions, names of variables, etc. Okay, so what I'm going to do next is give you, in each stage, just go through an example of what we have to do. Now, obviously, I'm not going to explain in detail what every stage does, because that's what the rest of the semester is for. But what I want you to get out of the next several slides is exactly what's happening, some concrete examples of input and output for each of these stages. So let's look at the front end first. We start with lexical analysis, which is the lowest level of analysis. So before we can read the entire program, we need to first focus on the letters and the words in the program. So lexical analysis, also called scanning, it takes an input program string. So remember, the input is just an ASCII file. Nowadays, it can be a UTF-8 file, but the general idea is that a program document is no different from any other document. It's just a string. And what we want to do is take this string and convert it into meaningful tokens. So let's look at an example. So let's say this is my input. The input is defining a variable f, and it's calling a function square root with an argument -1, right? So that's what's going on. At the lexical analysis level, all we're going to do is find the tokens. So we're going to say the first token is double. That's my first token, which represents, it's a reserved word in this language. Like double cannot be a name of a variable because it's reserved to be a type. And then the second token is the identifier, which is a variable f. Then there's an operator, which is a third token. The square root function is another identifier, because you can call a function anything. And then there are tokens for the structure. So there's the fifth token, which is a left parenthesis. Then there's an operator, which is a sixth token, so the minus sign. The integer constant is the seventh token. Then the eighth token is is the close parenthesis, and finally we have the ninth token, which is the end of this statement, which is a semicolon. So one question I want you to think about here is, what should be the token for a binary subtracting operator? So in this case, we have a unary operator. So this minus that's over here in this example, -1, is a unary operator. But the minus sign can also be used in a binary operators. So you can have 3 minus 2. And now you can see that the token is exactly the same, right? It's a minus in both cases. So what I want you to think about is, what should be the token output? Is it the same as this or different? That's a question I want you to think about. Once you have the set of tokens, the next phase is to take those tokens as the input. So this is a pipeline. So every stage in the pipeline produces an output, which is the input for the next stage. Syntax analysis then takes that sequence of tokens. So I showed you this sort of stream of tokens that gets generated, and then it parses it. This phase is sometimes called parsing. Essentially, it knows about the language specification in terms of what are valid programs, what are the structure of valid programs, and what are invalid programs. The key difference between the syntax and what came before is, in the lexical analysis, all it does is tell you what the individual tokens are, whereas syntax analysis, it assigns these tokens to a structure. So essentially, it's validating that structure. We have to have a data structure that tells us what is the valid program, and the way that we store a valid program in terms of its structural analysis is as a parse tree or a derivation. So let's look at an example. It's the same input, or part of the same input as before. So it's the right-hand side of that assignment that we saw in the lexical analysis case. So we're just looking at this function called of square root, which takes an input -1. So it might seem fairly simple, but if you want to analyze the structure, essentially what we want to construct is a proof. It's a proof that square root of -1 is valid. And the way that we construct this proof is by first checking whether, so we know that this square root of -1 is an expression. In fact, it's a very specific kind of expression. It's an expression that is a function call. So we know that it's calling this function called square root. Okay, so what do function calls look like? Well, a function call has to have the name of the function it's calling, which is an identifier. Identifier just means a name of some sort, like the name of a variable or function, any kind of name. And we know that square root is a valid identifier. The next thing you need for a valid function call is the open parenthesis. It's part of the syntax of this language. And then finally, what goes inside the parenthesis, so this part over here, can be any kind of expression. So I'm assuming here a simplified kind of syntax where you can have functions with only one argument, just for the sake of simplicity here. So this expression is now actually not just a generic expression, it's a specific type of expression, which is a unary expression. And this unary expression has a unary operator, a minus, and it has a expression after that operator. Again, can be an arbitrary expression. In this case, it's a specific type of expression called an integer constant, and that's 1. And then finally, to get a valid function call, you also need a close parenthesis. So without the close parenthesis, you would end up with a syntax error. So the question I want you to answer for this stage of syntax analysis is, can you draw a parse tree for this input? So square root of 256. So notice that in this case, this is an expression, and the question can be answered by trying to look at whether square root of 256 is a valid expression. So I'll give you a small hint here. You can see that the expression node in this parse tree occurs in 2 places, actually 3 places. And you can think of these 3 expressions as kind of a Lego block. This is a Lego block or expression, and it doesn't matter what's under underneath this. So you maybe have built a big Lego structure underneath it, right? It doesn't matter what's over here. What matters is that if somebody is expecting particular type of Lego block as an expression, matches. So this is a match, right? So if I'm expecting an expression that's over here and I provide an expression, then these two Lego blocks can click together and I get a valid expression. So hopefully that analogy helps in enabling you to answer this question that I've posed for you. The next stage is to take this sort of syntax tree, and you notice that there are certain things in here like these open parentheses, close parentheses. That's really not needed for code generation, right? That's just there to make sure that it's syntactically valid, but it's not very helpful when you're generating code. We don't generate code for an open parenthesis or a close parenthesis. So the next stage is to abstract away from the unnecessary details from the syntax analysis and get an output that's ready for code generation. So this is the last stage in the front end where we are going to produce an abstract syntax tree, which is then used for code generation. Now, this notation that you can see here is similar to the notation that we use for function calls, right? So if you have a function like foo, it takes two arguments, argument 1 and argument 2. This is very similar to saying that I have a function which is a method call. Its first argument is the identifier or the function name that I want to call, and then the second argument is what I'm passing as the value that I want to take a square root of, right? So this subtree over here is what is going to be the input to the square root function. You can write it in this function call notation. You can equally well write it using a tree as well. It's a very sort of simplified tree compared to the more detailed tree that we saw before. So notice that I have 1 and 2. So there's the two children that correspond to this one and this 2, right? The square root has no further children. That's a leaf node. Where a unary expression here has two children or two arguments using the function unary minus and a number, and then a number has one child, which is the constant 1. So you can either draw it as a tree like this, but what we'll be using is a sort of more conventional way of writing, which is this AST format that's shown over here, right? So that's what an abstract syntax tree looks like. In order to appreciate why it's called abstract, I want you to answer the question, how many nodes can you count in this abstract syntax tree compared to the concrete syntax tree from the previous slide? And in that comparison, I want you to focus on what was removed when we went to an abstract syntax tree. The next stage is semantic analysis. So before we sort of try to generate code, we want to look at the symbol table and the structure of the abstract syntax tree we have so far and ask the question, does it make sense? Very abstract level, what semantic analysis is to answer that question. So some of the questions, more specific questions about does it make sense are, is there a main function? Okay, we need a main function because otherwise we don't know where to start the execution of the program, especially in a compiled setting where you're creating a binary executable. If you're using a variable, is it declared somewhere? Are the operand types compatible? So for this one, let me use an example. So let's say you have an addition of two numbers. So let's say that you have 2 plus 0.1. In a strongly typed language, 2 might be represented as an integer, whereas 0.1 is represented maybe as a double or a float. When you look at this addition operation, there are two different addition operations, one for integers and one for doubles. So the idea behind semantic analysis here is to figure out which addition should I use. So the usual method is I take 2 as an integer and I convert it into a double, so that this one is a double now and this one is a double. And so I can call the addition function that takes two arguments. Both of them are the same type, right? So this step checks whether the operand types are compatible. In a similar way, you want to check whether an operand is just very similar to a function call. So you can ask the same question about functions. So let's say I have declared a function called foo, which returns an integer, and it takes double A and double B, right? So this is my function definition, and I want to call this function. So I'm calling this function with 2 and 0.1. In order for these two to match, I might have to promote 2 as an integer. So when you're going in this tree structure bottom up, 2 might have been analyzed as an integer. But in order to call this function, you need to promote it. So when it goes into this function, it's going to go in as 2.0 and 0.1. The next thing you want to do in semantic analysis is type checking, which really is one of the main advantages of having a statically typed programming language. A lot of bugs can be exposed simply by doing type checking. Type checking is also useful for code optimization, as we will see later. There's different types of semantic analysis that we need to do. There are some which are static. So these happen at compile time, and some are inserted into the code to do runtime semantic checks. So for example, if you have arrays in your programming language and you want to check whether you're accessing an array in a valid way, you can't really do that at compile time because you don't know which location of the array you might access. It's a dynamic property. When you're running the program, you might access an array. So a runtime semantic check would insert the code necessary into the executable that would do these kinds of semantic checks. So C famously doesn't do that for arrays. More modern programming languages do. Let's look at the compiler backend next. So let's start from a example source code that I'll use as an example throughout the code, for the code generation part. So it's a fairly simple program. What I want you to understand is its execution will start here in the main function. And what's the first thing it does is it has an if statement which calls this function foo, and this function foo is just always returning true, right? So it's a fairly trivial program. It checks the value returned by this function. It's always going to be true, and then it just prints the number 1, right, using this function printing. This is the program that I want to first analyze. So the first thing I do is I pass it through the front end. So the first step is lexical analysis. I get the tokens, then I would get the parse tree, and then I would get the abstract syntax tree. And the abstract syntax tree for this, even though it's a small program, is quite large, right? I don't expect to go through all of the details here. It's good if you go through the details to check that this is a valid abstract syntax tree at a high level for this input source program. So this source program is in my made-up programming language called decaf, by the way. And this is what we're going to be writing a compiler for in this course. The main things I want to point out in this abstract syntax tree is there is a function main, there is a function foo. Inside the main, there is an if statement, and the if statement calls foo, and then it takes a value and checks. So the if statement checks if it's true, which is always going to be true, and then it calls print int with this integer number 1. At a high level, you can see that this abstract syntax tree makes sense. Okay, the next step is to take this abstract syntax tree through a process which we will study in great detail in this course, but which will appear like magic right now. We create an intermediate representation. The main things I want you to look at here, because it's a lot of text, is that there is a main function. There is a function called foo. It's calling foo over here in this line, and then this br is a branch instruction in this intermediate representation. So note, it's not assembly language yet. It's very close to assembly, but it's an assembly language that's going to be common across many different computer architectures. It checks the value, and then if it's true, it executes this part, which is the part that's in the if true block here. And again, it's straightforward. It calls print int to print out the number 1. So you can see that there is, right from the source code to the abstract syntax tree to the intermediate representation, you should have the idea is doing the same thing. So if I take those blocks and take those branch statements and draw them as arrows instead, I can get a picture that looks like this. So this is exactly the same as here, except for every branch statement here and every function call, I have an arrow in this. So I've separated out the different blocks. When I'm calling foo, I have to go and execute this block over here, which is the foo function. And the same here, if it's true, it executes the if true block. And if it's not true, it executes the end block, which ends up over here, right? So it's fairly straightforward. All I've done is it's a more graphical way of looking at the intermediate code, which can be kind of a wall of text. It's hard to parse visually. Once I have the intermediate representation in that format, I can generate assembly language from it. Because you can see that this output is very close to assembly already, it's fairly easy to map this intermediate representation to an actual assembly language. So in this case, it's a mapping to x86 assembly. And if you look at this, broadly speaking, you can see that there is a foo, there is a main, and there is a branch statement which results in either a true or a not true or AND block, right? And you can see that when it's true, it's calling print int and it's printing 1. At every stage, we have gone from fairly high level representation in the source code, gradually making it more and more concrete. And in the end, we end up with x86 assembly, which is then passed through an assembler, creates the object file, and you can create an executable from it. The last stage in the backend is code optimization, which works on the intermediate representation. So we sometimes do optimization on the assembly, but most of the time we want to do our code optimization on the intermediate representation. If you look at the optimized version of the code, I'm not going to go through the algorithm that did it. We'll study that in more detail later. You can see that there is a main function here, but if you go back here, you can see that we are calling foo. Foo is always returning true. It's kind of pointless to call this function if it's always giving me the same value. So what I can do is actually get rid of this. And if I get rid of that, I know that it's true. I know that this if true is always going to be, it's always going to be valid. So I can actually remove this branch as well and then just go to if true. The only code I need to run is printing this number 1. And once I'm done with that, I return 0 from this function. So notice that I can eliminate a lot of this code in the optimization step, and I end up with this as the output. So notice that it just goes to if start, it calls the printInt function to print 1, and then it falls through and returns 0 from this main function to say that this function was successful. And if I convert that into assembly, you can see that this assembly is going to be much faster than the original assembly which we had, which involved a function call, an if statement. So you can see code optimization tries to remove instructions and as a result makes your code run faster. So here are all the stages of the compiler we just went through. The lexical analysis stage produces tokens. So this token stream goes into the syntax analyzer, which produces, so this token stream goes in, produces the syntax tree. The semantic analyzer looks at the syntax tree and uses the symbol table to do a bunch of semantic analysis. We create an IR from the abstract syntax tree, and then from the intermediate representation, we can optimize the IR to get an optimized version. And then it goes through the code generation and produces an assembly output, which can then be converted into an object file or a binary executable. So on the course website, there is a demo compiler, a very small compiler that goes through all of these stages. It does a very preliminary kind of code generation, and it's for a very, very simple language called EXPR, Expert Programming Language. It's a very absurdly simple programming language. I want to show you how easy it is to write a compiler for this very simple language by using these high-level compiler tools like Lex and Yak. So we're going to look at the description of this language. You can follow along by downloading the file expert.zip from the syllabus page of the course website. And if you unzip it, you'll find a bunch of files in here, like expert.lex, expert.y, and so on. And these are the definition of how I'm going to write my compiler. The compiler itself is for this very simple language. The language is of arithmetic expressions. The language specification is in this text file, expertgrammar.txt, and all it's saying is you can take two expressions and add them together. You can take two expressions and multiply them together. You can put an expression inside parentheses, and we'll see the reason why you might want to do that. And finally, an expression is this token number. This token is defined by the lexical analysis tool that bundles together a series of digits that are numbers and assumes that that's a single integer that you want to process as this abstract token called number. Let's first just build it. To build it, I just have to run this command make. Make takes the recipes that are built into the make file, and the make file contains the instructions to say, well, if you're compiling this YAC file, and then the first step to do is to run Bison. So remember, Bison is the GNU version of YAC, which is a specific tool that can help you generate code that does the syntax analysis for you. So you just have to write a YAC file, and I'll explain what's in that file. But once you write it down, it generates the C code for your syntax analysis part. In this case, actually, it does the code generation as well. Finally, the same thing is done for the lexical analysis. We're writing it in this high-level language called Lex, and it takes that definition and generates the C code for the lexical analysis part. We compile these different C programs together. We remember to put in the libraries for Lex and YAC. They are very absurdly simple, sort of short names. So -L loads the library, right? So that's what -L does. And the name of the library is just L. So there is a libl somewhere in the system that it knows where to find. And similarly for -ly, there is a libY somewhere in the system that it's going to link, and it takes the generated source files from the YAC and the Lex code that we wrote and generates a binary. Now this binary is a binary that accepts all of the arithmetic expressions that are specified. So easiest way is to see how. So let's look at the specification of arithmetic expressions in the YAC programming language / compiler tool. You can think of it as a programming language, or you can think of it as a tool that helps you build compiler. It's very similar to this high-level specification that we had in the text file. It says we have two expressions, we can add them together, and when you're generating code for it, it actually, instead of generating assembly code, it's generating C code, a C program, a small snippet of a C program that it runs every time you see a plus sign between two expressions that it has recognized as two expressions. Same thing for multiplication. So if you have two expressions that are multiplied, it generates a C code for multiplication. There is a rule that says you can put an expression in parentheses. As you can see, it has no semantic impact. It just takes the value of this expression, which is the second in this list, right? So this is the first, second, and third element in this sequence. And so it takes the second element, which is the expression, and returns that as the value for an expression that's inside parentheses. And finally, this is the base case of the recursion. You can have an expression be just a number. That's a C code that says take whatever the lexical analyzer tells me is a number and return it as the value of an expression. So that's the syntax. If you look at the lexical analysis, it just has 4 rules. The first rule says skip any blanks and tabs, so I skip white space. Notably, it doesn't skip a new line, so there's a special rule for new line which returns the new line itself. The second rule here says if you see a sequence of digits, so this is a regular expression which says if you have a sequence of digits, you have to have at least one digit. If you do have a sequence of digits, you assemble them together into one number. You pass it to this C function that takes a string containing a digit and converts it into an integer. and it's assigning it to this integer variable yyLval. It's a built-in variable. It has a funny name because it's sort of part of the language of writing this lexical analyzer. And then it returns a token called number, which is, as you saw, what is expected by the syntax analysis part in the YAC code. YYText is a string, so YYText 0 is just a character. So this is just C code. So the first element of an array of characters is just a character. And if it recognizes a new line, it returns that. And if it recognizes the dot is a special regular expression that matches any single character. So it just returns that character. This allows us to match things like the plus and the times and the open parenthesis and the close parenthesis. Okay, now that I have these, if I look at the expression.grammar.text, this is my specification, and I'm going to run my compiler for the expression language. You can see that any number can be a valid expression. So I can write 2 and it returns me back the evaluation of that, which is the number 2. So not earth shaking so far. If I type in 2 plus 2, it parses that string and it does the addition in C and returns the value 4 after doing that addition. Again, not so earth-shaking. It can do 2 plus 2 is equal to 4. It's great. So now let's do something slightly more complicated. What do you expect it would print out? Yeah, so it gets 2 times 2 first, which is 4, plus 2, which is 6. If I wanted to force it to do 2 plus 2 first, then I would put it in parentheses, and my specification allows me to do that. As you can see, I can put any expression in parentheses, and 2 plus 2 is a valid expression, right? Which is this in the specification. So I get 2 plus 2, I can put a parenthesis around it, and then multiply by 2, and I get 2 plus 2 is 4 times 2, which is 8. Okay, so you might say, well, this is a really simple language. All it does is arithmetic expressions. The first thing I want you to realize is that you can type in as long of an arithmetic expression as you want, and it will still work. There's an infinite number of arithmetic expressions. This very simple compiler does accept all of those infinitely many arithmetic expressions. The second thing it does is it only accepts what's in the specification. So it rejects everything that isn't in the specification. So if I say that I type in 3.2, it doesn't really know about floating point numbers. So it gives me a syntax error and quits. So if I run it again and I do 2 plus 2, and I forget to put the close paren, it gives me a syntax error and quits. So it does know about the structure of the program. So if I have 2 plus 2 times 2, that should work. But if I have 2 plus 2 and then times is a binary operator, so it needs 2 arguments. It gives me a syntax error and quits. So what I want you to do is try to come up with interesting examples and try to see if you can fool this compiler into accepting an arithmetic expression that isn't valid according to the specification that I've given. Okay, so finally, to wrap up, what we saw in this lecture is how we can go analyze a program and convert it to an executable, and all of the stages that happen in between. Each of those stages is what we're going to cover in great detail in the rest of the course. And the key idea here is to divide and conquer. The basic idea in these kind of tree structures. So if I look at analysis, what I'm essentially doing is producing these kind of tree structures. And the advantage of that is I can take what's underneath here and do code generation separately for each subtree. And then I combine them together at a larger subtree. Similarly, I can combine together these things recursively bottom up until I have analyzed the entire program. And at the top, what pops out is the code generation for the entire input source program. So we build one component at a time. As we study each of these phases, we'll see that there is a solid theoretical analysis that ensures we keep things simple and correct. So they are always provably correct components. This enables us to create a very complex piece of software, which is a compiler. It's quite complex, and it can accept any program in this programming language and generate code for it.